Hey everyone, welcome to your ultimate exam prep explainer. I'm your host, and today I'm fully stepping into my chemistry tutor persona because we are about to distill literally everything you need to absolutely crush your upcoming test on acids, bases, and salts. Whether you're cramming the night before or just wanting to solidify that foundation, you are completely in the right place. We're turning that heavy, dense textbook material into a fast-paced study guide. So grab a notebook, get comfortable, and let's lock down those high scores.
So, here's our game plan for today. We're tackling this in 5 bite-sized chunks. Spotting acids and bases, essential chemical reactions, the power of ions, mastering the pH scale, and finally, the secrets of salts. Let's get right into it.
All right, Section 1, Spotting Acids and Bases. This is your very first exam hurdle.
Okay, so let's lock in these fundamental contrasts. You probably already know acids have that sharp, sour taste, like a lemon, while bases are bitter and kinda soapy to the touch. But the real moneymaker for your exam? Litmus paper. Just remember this golden rule. Acids turn blue litmus red, and bases turn red litmus blue. Simple, right? Acids equal red, bases equal blue.
Now we've got to go beyond just basic litmus paper. Indicators are what tell us if something is acidic or basic. We have natural indicators like turmeric. You know, when a turmeric stain on a shirt turns reddish-brown after you wash it with basic soap. Then you've got synthetic ones like methyl orange and phenolphthalein. But here's a massive pro tip for your test. Examiners absolutely love throwing in olfactory indicators. These are things like vanilla, onion, and clove. Their actual smell changes depending on if they're hanging out in an acidic or basic medium. Definitely keep that in your back pocket.
Moving on to Section 2, Essential Chemical Reactions. This right here is the absolute meat of the exam.
Listen, if you only remember one single general formula from this entire explainer, make it this one. Acid plus metal yields salt plus hydrogen gas. This is basically the blueprint for so many questions you're going to face. A metal reacts with an acid, kicks out the hydrogen atoms to form a salt, and releases hydrogen gas. You can actually picture this classic reaction happening right now. Imagine dropping zinc granules into dilute sulfuric acid. The zinc displaces the hydrogen, forming zinc sulfate, which is our salt, while the hydrogen gas bubbles up and away. And oh, how do we test for that hydrogen? By bubbling it through a soap solution and bringing a burning candle close by. You'll hear this very distinct pop sound. Seriously, examiners are obsessed with that pop sound. Here's another classic exam trap broken down into 3 logical steps. When metal carbonates or hydrogen carbonates react with acids, you get a salt, water, and carbon dioxide. But how do you actually prove it's carbon dioxide? Well, you pass that evolved gas through lime water, calcium hydroxide. The carbon dioxide reacts with it to form a white precipitate of calcium carbonate, and that turns the lime water milky. Remember that exact sequence. Carbonate plus acid gives CO2, which turns lime water milky.
To tie up this reaction section, let's talk neutralization. This is when an acid and a base go head-to-head, totally nullifying each other to just produce salt and water. And hey, notice a brilliant pattern here? Metallic oxides also react with acids to give salt and water. Since they behave exactly like a base in this process, metallic oxides are actually considered basic oxides. And on the flip side, non-metallic oxides react with bases, making them acidic.
All right, Section 3, the power of ions. We're looking at the microscopic why.
So let me throw a tricky textbook riddle at you, one that shows up on pretty much every single test paper. Think about this for a second. Why does dry hydrochloric acid gas not change the color of dry blue litmus paper?
Well, here is the crucial answer. Acidic behavior relies completely on hydrogen ions. But hydrogen ions simply cannot separate from the HCl molecules if there's no water around. Without water, they can't form hydronium ions. That's H3O+. So if you have dry gas and dry paper, you have 0 water, which means 0 hydronium ions, and absolutely no acidic behavior. This setup perfectly illustrates that point. An acidic solution mixed in water easily conducts electricity and lights up a bulb. Why? Because the water lets the acid dissociate into ions, cations and anions, which carry the electric current. If you swapped out that acid for, say, a glucose or alcohol solution, the bulb goes totally dark. Even though they have hydrogen in them, they just don't dissociate into ions and water.
So to wrap up the power of ions, let's cement these 2 definitions.
Acids produce hydrogen or hydronium ions in water. On the flip side, bases generate hydroxide ions, OH- in water. Oh, and remember, bases that dissolve in water get an exclusive VIP name, alkalis. Basically, all alkalis are bases, but not all bases are alkalis.
Next up, Section 4, Mastering the pH Scale. This is chemistry in the real world.
Looking at these universal indicator colors, the pH scale ranges from 0 to 14. That P actually stands for potens, which means power in German. It's literally the power of the hydrogen ion concentration. 7 is perfectly neutral. Think pure water. Anything below 7 is acidic, and the lower that number gets, the higher the hydrogen ion concentration. Now, as you go up from 7 to 14, that shows an increasing hydroxide ion concentration, meaning a much stronger alkali.
Now, commit this specific number to your memory right now, 5.5. Why this number? Because 5.5 is the exact pH threshold in your mouth where your tooth enamel starts to corrode and decay. When bacteria in your mouth break down leftover sugars, they churn out acids. If the pH drops below 5.5, your enamel, literally the hardest substance in your body, starts to dissolve. It's exactly why we use basic toothpaste to neutralize that acid. Crazy, right?
Okay, these natural acid pairings are prime targets for applied chemistry word problems. You definitely need to know them. Vinegar has acetic acid. An ant or nettle sting hits you with methanoic acid, which, by the way, is exactly why rubbing a mild base like baking soda on a bee sting actually stops the pain. Citrus fruits like lemons and oranges are packed with citric acid, and tomatoes have oxalic acid. Just take a mental snapshot of this list. Finally, we've made it to Section 5, The Secrets of Salt. And no, it's way more than just table salt.
Check out the pattern here. Salts actually belong to families, and they inherit their pH levels from their parents. A neutral salt comes from a strong acid and a strong base neutralizing each other, landing smack on a pH of 7. But an acidic salt, that's formed when a strong acid bullies a weak base, dragging the pH below 7. Basically, the stronger parent dictates the final pH of the salt family. It's a fantastic shortcut for predicting salt properties on a multiple-choice test.
To wrap up our explainer today, I want to leave you with this really fascinating planetary question straight from the text. The atmosphere of Venus is smothered in these thick, yellowish clouds of sulfuric acid. Based on everything we've just learned together about extreme acidity, pH scales, and that super narrow pH window living organisms need to survive, do you think life could even exist in those clouds? It really challenges you to see how these chemical properties apply way beyond just your exam, out into the entire universe. Keep reviewing these concepts, good luck with your studies, and you are absolutely going to crush that test.